Today we're going hands-on with one of my favorite parts of Rust's concurrency toolbox, message passing with channels. If you've ever wanted threads to talk to each other without sharing locks and mutable state, channels are your new best friend. We'll build from a tiny hello all the way to a mini pipeline with multiple producers, timeouts, and bounded queues. To follow along, you must know how concurrency works in Rust. If you don't know, I would highly recommend you to watch previous videos of the series. Let's start at the smallest possible example. One thread sends a message, the main thread receives it. We'll use the standard library's mpsc module. mpsc stands for multiple producer, single consumer, many senders, one receiver. This is inter-thread communication using channels. A channel is created with a transmitter, TX, and a receiver, RX. A new thread is spawned, and the transmitter is moved into it. The spawned thread then sends a message, hello from worker, through the channel using tx.send. The ownership of the string is moved into the channel, so the variable message can't be used again in the spawned thread. Meanwhile, the main thread waits for a message to arrive by calling rx.receive. When the message is received, the main thread prints it. Notice two things already. First, send takes ownership of the value and moves it across the boundary. That eliminates data races. Once you send it, you can't touch it anymore on the sender side. Second, receive method blocks the main thread until a message arrives. If you comment out the sender, receive method would block forever, or return an error if the channel is closed. Let's make the conversation a bit richer. We'll send multiple messages and learn a neat trick. Receivers are iterable. When all senders are dropped, the loop ends automatically. This is great for Graceful shutdown. Again, we create a channel with a transmitter, TX, and a receiver, RX. A new thread is spawned, and a clone of the transmitter is moved into it. Both the main thread and the spawned producer thread send messages to the channel. The spawned thread sends a series of tick messages, pausing between each. After the main thread sends its message, it drops its transmitter, TX, signifying it won't send any more messages. The for loop on the receiver, RX, continues to receive messages until all senders, the one in the main thread and the one in the spawned thread, have been dropped. This ensures the loop gracefully terminates. You see how for message in RX just ends? That's the moment the last sender is dropped. This pattern is how you signal no more work is coming. I promised multiple producer, single consumer. Let's fan out or distribute work across several threads and fan it or collect the results back through one receiver. We'll also demonstrate that sender is clone, which is how we get many producers. Here a loop spawns 3 worker threads, and each thread receives a clone of the transmitter. Each worker thread then sends 3 messages to the channel. After spawning the threads, the main thread drops its original transmitter, TX, which is crucial. This drop signals to the receiver that no more messages will be sent from the main thread itself. So the for loop on the receiver, RX, can gracefully terminate once all messages from the worker threads have been processed. The main thread then waits for all worker threads to finish using handle.join. Finally, it iterates through all received messages and prints them. You'll probably see messages interleaved in a different order each run. That's expected. The channel preserves order per sender, but the receiver intermixes messages from different senders as they arrive. Blocking receive is fine, but sometimes you want to peek without getting stuck. For that we have try receive and receive timeout. Let's demo both. Here we set up a channel and spawn a thread that sends the number 42 after a short delay. The main thread first tries to receive the message immediately using rx.tryReceive. Since the other thread hasn't sent the message yet, this call returns an error, indicating the channel is empty. Then it uses rx.receive timeout, which waits for a maximum of 500 milliseconds for a message. Because the message arrives from the spawned thread within this time limit, receive timeout successfully receives and prints 42. Try receive returns immediately, great for event loops. Receive timeout lets you wait up to a deadline, which is perfect for responsive services. Unbounded channels are nice, but what if you want backpressure so a fast producer can't overwhelm a slow consumer? That's what sync channel is for, a bounded synchronous channel that blocks senders when the buffer is full. If you pass capacity 0, it becomes a rendezvous or meeting point. Every send waits for a receive. Watch the logs. You'll see sends pause when the buffer fills, then resume as the consumer drains it. That's backpressure in action. Here we are using a bounded synchronous channel, sync channel, to manage communication between a fast producer and a slow consumer. The channel is created with a capacity of 2. The producer thread sends 5 messages, A through E. The channel's buffer can hold only 2 messages, so the producer will block on its third send, C, until the consumer starts receiving messages. The consumer thread intentionally waits before starting and then processes messages one by one with a delay, demonstrating the backpressure effect of the bounded channel. This ensures the producer doesn't overwhelm the consumer by sending messages faster than they can be handled. Let's talk about error cases for a moment, because robust programs handle them. If the receiver is dropped, send returns error containing your original message. If the sender side is all gone, receive returns error, receive error. Let's surface both explicitly. The first part shows a tx.send call failing after the receiver, Rx, has been manually dropped. The send method returns an error containing the value that was not sent, 10, which is then recovered and printed. The second part shows the opposite. Rx.receive call fails with an error after the sender, tx2, has been dropped. This signals to the receiver that no more messages will ever be sent, and the channel is closed. That ability to recover the unsent value from SendError can be useful. Maybe you want to log or retry elsewhere. Let's build something that looks like a pipeline. One stage generates numbers, a worker doubles them, and we collect results in the main thread. 2 channels, one for tasks, one for results. This is a classic producer-worker-consumer pattern using 2 channels. The first channel, txjobs rxjobs, is for jobs. The main thread acts as a producer, sending numbers from 1 to 10. The worker thread receives these numbers, processes each by multiplying it by 2, and then sends the original number and the result through the second channel, tx results rx results. The main thread then acts as a consumer of the results, iterating through the rx results channel and printing the input-output pairs. Crucially, the producer drops txjobs after sending all the work, which causes the worker's for loop to terminate gracefully. Elegant, right? No locks, no shared mutable state, just messages flowing through stages. This scales nicely. There are 2 ways to scale. First is multiple producers. To have more threads generating jobs, you'd clone txjobs and give a copy to each producer thread. Second is multiple workers. While the standard mpsc channel in the code is for a single consumer, rxjobs, you could have multiple worker threads. To do this, a common pattern is to have one consumer thread that receives all the jobs and then distributes them to a pool of worker threads. Alternatively, specialized third-party crates like Crossbeam Channel provide channels that allow multiple threads to receive from the same channel, enabling true multi-consumer setups. Now I want to touch a subtle but crucial topic. What can you send through a channel? The type T must implement send so it's safe to move to another thread. Most standard types do. But something like RC is not send. This is by design. RC is single-threaded. Let's try to send an RC and watch the compiler save our day. In this code, we attempt to send an RC, reference-counted, value between threads, but it won't compile because RC is not thread-safe. The compiler will complain that RC doesn't implement send. The fix is to use thread-safe counterparts like arc if you need to share read-only data across threads, or to move own data like string directly. Remember, channels move ownership. That's a huge reason they're safe and ergonomic. Another ergonomic pattern is to have your worker threads send back results or status. Let's simulate multiple workers returning their partial sums to the main thread. This is a great way to do fan-out work, fan-in results. This is parallel computation and result aggregation using threads and channels. We create a channel and spawns 4 worker threads. Each worker receives a clone of the channel's sender and performs a distinct, computationally intensive task, summing numbers up to 10,000, with a unique multiplier based on its ID. Once a worker finishes, it sends its partial result, a tuple of its ID and the calculated sum, back to the main thread through the channel. The main thread then iterates over the received results, storing each partial sum in the correct position in a totals vector. Finally, after all workers have completed and the channel is closed, because the original sender was dropped, the main thread calculates and prints the final grand total. You can visualize how this maps to real tasks: parsing files in parallel, processing images, aggregating statistics. Each worker owns its chunk, then reports back via a channel. Now for a tiny quality of life tip. If you know you'll just stream values and don't need fancy control flow, iterating the receiver is the cleanest. If you need to do periodic work while waiting, receive timeout in a loop gives you a heartbeat. Here's a sketch of a responsive loop that does periodic, tick work while waiting for messages. Here a new thread is spawned to act as a producer, sending two messages, event A and event B, at different intervals. The main thread, acting as the consumer, enters a loop that uses rx.receiveTimeout. This method attempts to receive a message for up to 200 milliseconds. If a message arrives, it's printed. If not, the match block handles the timeout error and prints a tick. The loop continues until the channel is disconnected, meaning the producer thread ends and drops its sender, at which point the disconnected error is handled and the loop breaks. This is a nice pattern for services that should remain alive and responsive, doing background maintenance while waiting for events. All right, let's zoom out. With channels, you model concurrency as ownership transfer. One thread owns the data. When it's ready for the next stage, it hands ownership off by sending it. No shared mutation required, no locks, no footguns. The type system helps further. Anything you send must be send, so it's thread safe to move. And the mpsc flavor, many senders, one receiver, maps naturally to fan and aggregators, pipelines, and work queues. Use channel when you want unbounded queues, sync channel capacity. When you need backpressure, try receive and receive timeout when you need responsiveness, and drop your last sender to signal completion. If you need multiple consumers, you can build that pattern with a dispatcher thread, or reach for external crates built for broadcast or multi-consumer semantics. But for a huge number of programs, SDD's channels are a perfect fit. If today's session clicked, tell me in the comments what pipeline you're going to build first: file processing, crawling, data transforms?